try to put some math, and then I try to take some math out, and then I try to put some art in, and then I took something out, but I hope that each and every one of you will find something interesting in this soft field. And I have a rather ambitious plan, but let's see whether I can do it in half an hour or less. So I will start with tessellations, and then I will try to explain correspondences between knots and graphs, and give a very, very brief introduction for Scott and Ted and maybe others into Conway notation, which is the absolutely best notation for knots and has not been exploited much. And I will illustrate the new way of classifying knots and links according to into families. So, why did I use the word cut in the title instead of tessellations? Well, here there are some definitions of tessellations that I'm sure that we are all familiar with. But for example, the second one says that it's a collection of shapes which fit together to cover a surface without overlapping or leaving gaps. Well, if I think of it as cutting the surface, then I don't have to worry about overlapping. So it's half of the work. You just need to worry not to have anything left. So I just want to emphasize that I'm going to be working with plane tilings of various two-dimensional planes, and I'm going to be using polygons only, but not polygons like this. I do want my tessellations to be edge to edge, so there is going to be no additional vertices in between, like on an edge of a different polygon. So behind all the pictures I will show here, there's a Mathematica package set that's been available since 2002 on the Wolfram Research website and on my website. And what this package uses as an input is a vertex symbol. So I guess that this may be interesting for educators. I had really, really good feedback when I was showing this to kids. But what the vertex symbol is just an envelope of numbers, integers. And you let the kid give you 2 or 3 numbers, and what the program gives you is a tessellation. Well, not every combination will give a tessellation, but if you're lucky enough, you will get one. So what this thing shows here, what the vertex symbol is in this case is just 4, 6, and 14, which means that around this vertex you want to have a square, a hexagon, and a 14 gone. And there are some nice theorems that I'll try to avoid math, but would basically say that if we are able to fit these polygons around one vertex without gaps and overlapping, then they will cover the whole plane. So that's very convenient. And indeed, here is the whole plane, the whole hyperbolic plane. And just as another illustration, so this is a vertex symbol 3, 6, 4, 6, so that we all know what we're talking about. So what the program does, these are just various certification of different plane tilings. Where I'm going to be is I can create all of these here, and what the program does is that it usually creates tessellations in such a way that you have a same constellation of polygons around each vertex. It can do more, but it's really, really slow. What's good about this approach of having just a vertex symbol and not something else as an input, first because the input is easy, and the second is that you can get non-uniform tessellations. So, given a vertex symbol, our code will try to come up with a solution, and then that solution is basically going to be a graph, right? And then it's going to try to embed a graph on in one of the geometries, on some plane. And here we see that if around each vertex we have a triangle, like 4 triangles and a square. This is just a distillation of a sphere, which can be thought of as a polyhedron. And then if you have 4 triangles and a hexagon, around each and every vertex we'll get a Euclidean distillation. And then if you have 4 squares and a heptagon, it's going to be a hyperbolic distillation. So, of course, we can play with colors. Of course, colors have meaning here, but they just represent the same. So, polygons that have the same color are in the same orbit. And then depending on what the sum of angles around each vertex will determine whether it's a spherical or a Euclidean or Riemannian. So, we've all seen Escher's tessellations. So what's behind them? It's a sort of reverse way of thinking about it. So, what I would think of here is that, well, let me just show you. So all I'm claiming is that behind this tessellation here, there's this tessellation by a triangle and a square and a triangle and a square and a triangle and a square around each vertex. And, I'm sorry. So this is the tessellation that's behind it. And if you want to go back, we find the fundamental domain. And then depending on our creativity, we come up with a nice motif, and we get a nice tessellation. So I was playing with this a little bit, and I apologize about the colors. But when I look at it, it's actually, for me at least, although I've created this program, it's very hard to see the underlying tessellation. And one nice or not nice thing that's worth mentioning is that symbols of tessellations are not in one-to-one correspondence with tessellations. So for one vertex symbol can have multiple realizations. Okay, so how do we go around this? We just find the fundamental domain. We pick some nice or less nice motif to put inside here, and we get the tessellation. Depending on the type of motif and whether it's more or less symmetric, you obtain these tessellations. And so one easy way of thinking, well, symmetry is beautiful, but what I often find is that it's not boring, but it looks, well, anyway, I find this one more interesting. And the only difference between this one and this one is that this constellation of triangles has been moved from the center of a disk. Okay, so there are many ways of producing different tessellations from a given one. And here are just some examples of connecting in centers of polygons in various ways. And for example, this one is interesting. So if around each vertex you have 7 triangles, if you perform this kind of operation, you'll have a tessellation which is shown in like blue wired model, which has 3 heptagons at each vertex. So I'm studying knot theory. So for all of you who don't know it, so all the roads lead to knot theory. So does my talk converge to them. So this is not mine, but I don't know how to properly credit it. To whom should I credit it for? This is a way to, if you pick just a finite part of our tessellation, well, we can construct a knot from it. And this is one of the beautiful Celtic knots by George Bain. So now comes the scary part. So knots are usually very involved, like messed up and so on. Just think of yarn when you're knitting, or DNA molecules, or polymers, or something. So, but there's a very, very, very nice way of constructing them, and it was invented by Conway. And this is how he starts. So the main building block is, well, if we work with knots, we can work either in 3 dimensions or in 2 dimensions. So just for the simplicity, I'll project knots in 2 dimensions. We have to pick a nice projection which has no triple points and so on and so on, but let's assume that we did all of it. So we can construct knots from something that's called a tangle. And it's just in 3 dimensions, it's a sphere, here it's a disk, which has 4 arms, or 4 connections. So, and then you can put whatever you want in here. So all that matters is that it has 4 arms. And for example, you can imagine putting something that's denoted by 0, just here like this, or one of the crosses, positive or negative. Okay, so now we have a main building block, and how are we going to build our knots? Well, let's introduce some operations. So first, given any tangle, any 2 tangles, we can just connect them like this, or we can reflect one of them along the diagonal and then connect them in the same way as here. So this operation is called sum. This operation has a name. Does this show? Okay. So this one is called a sum, and this is a product. And then if you reflect both tangles and connect them in the same way, this operation is called a multiplication of tangles. The difference between real and mathematical knots is that real knots are usually open-ended. Just think of your shoelaces or DNA molecules, but in math, we do like to close them up. So what we can do, if we're given a tangle, we can choose either numerator or denominator closure. And I think the picture says enough. Then what's shown in the bottom right part of the slide is just the way if you have a positive crossing here and a positive crossing here, and we sum them up, well, we're going to get something that's going to be denoted by 2. And this can be, again, plotted as a tangle. So it's a sort of recursive process. You have a tangle, you're building it up, like so it's shown on here, like in here. We start with this 2. We can add 1, and then again 2, and so on, and the symbol is 2, 1, 2. So this seems like a rather nice way to construct knots. Unfortunately, not all knots can be obtained in this way. But Conway did think of a way to obtain other knots. I mean, all knots. So the top left picture shows polyhedral knots. So just think of them as, you basically can think of them as 4-valent graphs, which just collapse all of the circles into a point. And that's what they are. So polyhedral knots are knots that can have no diagonals. So nothing that looks like this. This is a diagonal or a half moon or something. So, but of course, in order to use Conway notation for polyhedral knots, this is slightly inconvenient. You have to know how this picture looks like and how are these elves oriented inside the circle. Okay, but these are all technical details. Of course, we have found Slavic outline and myself. This is a drawing work with Slavic. But these are general things that I'm still talking about, that I've talked about so far. So basically, the first picture you see here, 6 star is equivalent to this top picture here, and then 8 star to this picture here. And this is really the way to think about them as just as 4-valent graphs. Okay, but thinking about them as 4-valent graphs is nice, but it will not give us much because we want to construct all knots. So given a polyhedral 6 star here, well, let's just try. We can put a positive crossing here, and let's say just a 2 here, or a 1 here, and we have obtained, and this is exactly how we get notation. So here we have 6 star, and then whatever the first tangle was, we have put number 2 in there, just 2 positive, and then in this next one, it's 1 positive crossing, then again 2, and then 1, and you can follow it on the picture. Okay, so this is nice we can construct knots. Distinguishing them is still hard, and again, one knot can have many copy symbols associated with it. So that's not good, but the way that knots are classified so far is just according to number of crossings on a minimal diagram. So what you need to do to classify them, you have to figure out what's the minimum number of crossings, and so on. And it's hard even to determine, and this is all that this picture of short animation tells us. It's even hard to see how many components a knot has. Well, a knot with many components is called a link. So let's see what we can do. We can classify knots according to number of components, according to number of crossings. There are some other ways, non-alternating, or let's say rational or polyhedral. But let's look at them more precisely. So what you see here is a knot that's denoted by 2, 2. So here you can recognize this symbol, this one diagon and the other diagon, and they're sort of organized in this perpendicular way, like they're perpendicular to one another. Okay, and then look at the next picture, the middle one. What we have here, we have 3 diagonals, 4 crossings, vertically and then 4 crossings horizontally. So basically it's the same shape. It's just that we do increase number of twists in the middle. That's the idea, and what's nice about it is that various knot invariants, such as, well, first of all, symbols are very easy to see. So this one is denoted by 2 space 2, this one is 4 space 4, this one is 6 space 6. And then I put here some like basic invariants, but you don't need to get into it. For example, unknotted number that's denoted in pink. That's the number of crossing changes that you need to make to get from your knot to an unknot. So here, unknotted number is 1, and you can just imagine that you just switch this one, you put it behind this one, and it's going to unwrap. So the first one has unknotted number 1, the second one unknotted number 2, and the third one unknotted number 3. So that inspires Slavic Javelin to define families of knot symbols given in Conway notation, and the rules of this game are really, really easy. So what you do, if you're given a symbol of a knot, basically it has n elementary tangles, just n symbols. So let's think about here, it's 2, 2. We can replace each even number with a bigger. So we're basically just going to add 2. So even numbers will stay even, odd numbers will stay odd, and single positive crossing will stay single positive crossing. And here are just some examples. And it's, for example, it's just easy to see that, let's say, a number of components stay the same. So 3, 3, and 5, 5 belong to the same family, and there are 2 components. Okay, so still, what are we going to do with these families of knots? Well, I'm going to skip all math, and I'm going to just give a reference to the paper. The thing is that Slavic and I were able to obtain general formulas for families of knots and links. So you don't have to compute it. For example, for famous Jones polynomial that was invented in 1983, and the way to compute Jones polynomial given a knot is if you have a non-knot that's just a circle, the value of the Jones polynomial is 1. Well, given any other more complicated knot, and let me just, sorry, I don't have to, I think. Yeah, I have only 5 minutes, so I'll speed up. So the way that you would deal with this is that you have, it's going to be a Laurent polynomial in a variable t, and you're going to have just half powers of t, you can change the variables. So the thing that you need to do is, starting with this knot, you have to replace each positive crossing, let's say this one, either with 0 smoothing, so this one, or negative smoothing, which means it will just change over and under relation here. And for this one it's really easy, because you can see this is just an unknot and this is just an unknot. And then you plug values 1 and 1 into this substitution, and you obtain the value of Jones polynomial of this particular link called coupling. Okay, so it seems like a lot of work to do this. But there's a nice way to compute Jones polynomial from the Tuss polynomial. And Tuss polynomial is a polynomial defined on graphs, and there's a nice substitution. Tuss polynomial is a 2-variable polynomial, but if you put substitution x and 1 over x, you'll get, well, I guess it should be t and 1 over t. We'll get the value of the Jones polynomial. So since I'm running out of time, let me just say that what we used here, here's the definition of Tuss polynomial, and it just depends on, given your graph, you take all possible subgraphs, and then you count number of components, connected components, and you plug it in this formula. See? And there's a nice property that this polynomial satisfies, that is this deletion subtraction formula. So there's a recursive formula that relates Tuss polynomial of your graph with Tuss polynomial of graph that's obtained by just deleting, let's say, this edge E and getting graph G minus E, or let's say just by contracting this edge. So this edge E becomes a small loop, and then it's right. So these are generally saying polynomial, but you will say, okay, I have Jones polynomial of a link, and I have plus polynomial for graphs. So how do I assign a graph to a link? And vice versa. So here's the way. I'm sorry, the animation. Given the triple knot, which is shown here, you color, let's say, the outside region black, and all the neighboring regions, meaning regions that share a crossing with it, black, and everything else is white. Okay? So what we have here is that this region is black, and then the one that's connected to a crossing with it is black, and these are white. So let's assign a vertex to each white region. These are red dots. And let's connect red dots that represent two different regions by an edge if these two regions share a crossing. So as you see, we just get a triangle here. And here's another example. Given a more complicated, well, three-component link, we can get this graph. Okay, and then here's the way to obtain plus polynomial shown in red of a triangle using the addition subtraction formula. If you make a substitution, we'll get a Jones polynomial of triangle. Another specialization of plus polynomial is chromatic polynomial, and it's obtained just by substituting 0 for the second variable. Let me just emphasize that chromatic polynomial counts the number of different colorings by lambda edges. So what's shown in this picture is a way to color this particular graph with 3 different colors. And the rule is that 2 vertices that are connected by one edge cannot be colored by the same color. Okay, time is nonsense. So what we have on this side here is a basic polyhedra 8 star. What we have here is its corresponding graph, which you can just think of it as a pyramid which has a square as a base. You just lift this middle point up. And here's a general formula that for its plus polynomial of its graph, and the rest of the formulas are in the paper Jones and Polynomials of link families and can be found in archive. So here, let's see. So here's the correspondence. For a basic polyhedral knot 6 star, this is the corresponding graph. So here's one vertex, second, third, and fourth, and so on. So based on families of knots, I have defined this nice family of graphs, and then, of course, I can think of their polynomials. And these are just, I have general formulas for them, and I've used them to obtain nice visualizations using software, Polynomiography. And for example, you can see here that the degree of polynomial jumps by 1 because we have the number of regions decreasing of different colors. And the same thing for Jones polynomials. Okay. And then if you just use Mathematica and play around with colors, these plots represent zeros of Jones polynomials of various classes of knots. So on the left, we have all rational antichiral knots, so knots that whose left and right antichiral knots. And then the other one is rational sorting, I'm sorry that I did not mention. And these are stellar basic polyhedra. These are generating links, and these are rational generating and source links together. Thank you for your attention. While I'm announcing the talk, I would just like to present something that was done by my friends who are architects. When I showed them like a week ago the idea of families of basic polyhedral knots. So these green ones, ugly ones, basically represent, like, if instead of just one crossing at each vertex, you put something more complicated, then you of course increase the complexity of your knot. So I hope you will enjoy I think there's like 3 more minutes of this talk, and I hope that this illustrates nicely how you can switch from
So, how do you know that you only need those templates to generate all knots?
How do you use those then?
Templates, the Conway templates, can you generate all knots by rational tangles?
Oh, it's not only 10.
Template. The Conway template, the draft template. Why?
Oh, it's in this paper.
Yeah, I know, but
From 7.
why wasn't it true? I can't.
So okay, because there's a so this particular correspondence is based on correspondence of graphs, but not the one that I correspondence with graphs, but not the one that I explained. So basically, what you do, if you take any rational knot, so the one that can be generated by moves without polyhedra, when you start collapsing diagonals, it collapses into a point. And then if you take something that's not oh, I missed my favorite part. Anyway, so if you take polyhedral knots and you start collapsing them, you're going to get various polyhedra. That's how polyhedra were obtained. So there's a system in correspondence between all four-valent non-isomorphic graphs and families of basic. Well, basic polyhedra, not families, just basic polyhedra.
So your result says that if we know the template and we know the rational tangles of each vertex, that we can use those data to compute the Jones polynomial.
Okay, so my results are like in 2 different papers, and this one is just general formulas for Jones and so on, and it's nice because it works for the infinite family, and you don't have to worry about how many crossings your knot has. But the main idea behind it is that you can basically determine how some invariants, including knots, quantum homology, will behave inside the family. Is it going to stay constant, or is it going to behave in a nice way, like increase by, it's also going to increase or 3 parts or something. And that's nice about it, because then you get a general result. So we use that for get non-quasi operating. These are also various families of nonlinear links presented in this way, with just 2 orthogonal.
Is there another way to catalog knots, like get inside the knot and keep track of how many left turns you take, or how many degrees, or keep track of magnetic north? And I don't know, you know.
So knots are in general 3-dimensional objects. It's just that it's human nature. Oh. These are people whom I need to thank for having this. Knots are typically 3-dimensional objects, and there are different ways of denoting. You cannot measure just number of right or left turns. You need to take care of like over and under relations.
So you don't think that a knot is not a one-dimensional, what's the word, manifold embedded in a 3-dimensional space?
Yes,
it is.
That is what it is.
It is, but like if you think of it as the projection, I mean.
So but there's nothing, I can't ignore the 3-dimensional, there's nothing about the one-dimension thing that I can keep track of that leads me to a description of knots. I somehow...
The problem is that the geometry that you're trying to think about, say traveling awful long enough, keeping track of a tangent in a normal, is not an invariant of the knot type. So the string is allowed to move. It's an object topology. It's not a geometric object.
Okay.
Let's talk more about it. I think the taxis are waiting for us in front of the building, and I think we all have they'll take us to downtown Princeton, and